Hi everyone. In today's class, we shall solve some problems on first law thermodynamics and isothermal and adiabatic processes. And the first problem is this one. The problem is a certain volume of dry air at NTP is expanded reversibly to 4 times its volume. First condition isothermally and second condition adiabatically. Calculate the final pressure in each case, assuming ideal behavior. And there was a hint given. What is that? Cp over Cv for air is 1.4. So here we are going to find out the final pressure in isothermal case, in adiabatic case. What we have done in the last class, to the final same value, the pressure in the state at the state that reached through adiabatic process always smaller than the pressure at the state that reached through isothermal process. Let's also uh, get that fact from this problem. Okay, now let's do for the problem A. What is that? That is isothermal process. The problem A is isothermal process. So as it is isothermal process, there is no change in the temperature. We know that. And here in the relationship between pressure and volume in isothermal process is P1 V1 equal to P2 V2. So here what we do, we know the initial value. Do we know it? There was no number given. Therefore we say initial value V1 equal to V2, and he said the final value is 4 times its initial value. Therefore I can write V2 as 4 times V1. So now let's see, it has a initial pressure certain volume of dry air. Calculate the final pressure in each case. Let's take initial pressure as something uh, 1 atm. Let's compare what is the final pressure in isothermal process and adiabatic process. Okay, now if we substitute here, what we require? We require P2. Therefore, P2 equal to P1 times V1 divided by V2. So that's going to be 1 atmosphere times, what is the V2? V2 is 4 times V1 divided by V1. So if we cancel and V1, we have, sorry, I made something wrong here. The initial value is V1, the numerator is V1, and the denominator is 4V1, because in the denominator we have a V2. So here and V1 cancels out. Now we have a final pressure P2 as 1 divided by 4 atm, that means 0.25 atmospheres. This is the pressure in isothermal process. The state that reached through isothermal process has a pressure of 0.25 atmospheres, and the volume at the final state is 4 times the volume at initial state. Now let's see. And what about the temperature? Obviously, as it is an isothermal process, there is a drop in the temperature. Now let's go for the adiabatic process. In the adiabatic process, we have a relationship between pressure and volume as PV power gamma equal to constant, and for temperature and volume, T times V power gamma minus 1 equal to constant, and pressure and temperature relationship is T times P raised to the power of 1 minus gamma over gamma is equal to constant. So here let's find out what is the pressure. So what is the relationship here between the pressure and volume? That is PV power gamma equal to constant. And what is the gamma? Gamma is Cp divided by Cv, that is 1.4. We already know that. So if we write the first and final and initial state conditions, we get P1 V1 power gamma equal to P2 V2 power gamma. And if we simplify, we get P1 divided by P2 equal to V2 divided by V1 power gamma. What should we do here? Here we should do something. What is that? So we know V2 is 4 times V1 and V1 equal to V1. So now let's plug it, and we know P1 is 1 ATM. So therefore now what I do here, I do, okay, so here 1 ATM divided by the final pressure we don't know, that's equal to, what is V2? V2 is 4 times V1 divided by V1 power, what is the gamma? Gamma is 1.4. So that gives us, so 4 and 4 cancels out. So we get 1 atmosphere divided by P2 is equal to 4 times 1.4. So next what we get here? We get pressure P2 is equal to 1 atmosphere divided by 4 power 1.4, and if we substitute in the calculator, let me do with the calculator, 1 divided by 4.14, 1 divided by 4 power 1.4, that is 0.143 ATM. Now let's compare the state that is reached in isothermal process has a pressure of 0.25 atm, and that state that is reached by adiabatic process has 0.143 atm. It is clearly a supporting evidence for what we have discussed in the last class. And one more important thing here, in adiabatic process temperature changes. Now let's find out how the temperature changes in the adiabatic process. Now let's take, what is the relationship between temperature and volume? That is T1 divided by T2 is equal to V2 divided by V1 power gamma minus 1. Now let's plug here. Okay, let's take the standard temperature, that is 273 Kelvin as the initial temperature, and T2 we are going to find out. Now here V2 is 4 times V1 power divided by V1 whole power 1.4 minus 1. So that gives us 273 divided by T2 is equal to, V1 and V1 cancels out, we have 4 power 1.4 minus 1 is 0.4, and what we get finally, we get temperature T2 273 divided by 4 power 0.4, and if we use the calculator, so let's see how much we get if we use the calculator. So 273 divided by 4 power 0.4, that's 157 roughly. So that means in adiabatic process, not only the final pressure is smaller than the pressure achieved through isothermal process, but also there is a drop in the temperature. So that means adiabatic expansion always accompanied by cooling effect. In fact, we will study that in the next class, that is known as Joule-Thomson effect. Okay, now let's go for the next problem. Okay, calculate Q heat, W work, delta U internal energy change, delta H enthalpy change for the isothermal expansion of 1 mole of an ideal gas from an initial pressure of 1.0 bar to final pressure of 1.1 bar, constant temperature 273 K. So here the major hint points are constant temperature, that indicates that is a isothermal expansion, that is already there here, and one more important word in the problem is reversible expansion. So therefore here in this is isothermal expansion, therefore temperature is constant throughout the process. And we know that internal energy, so this problem is given U, but we have used so far E as internal energy, which is a function of temperature. Enthalpy is also a function of temperature. Therefore, these two factors do not change as temperature is not changing. Delta E is equal to 0, delta H is equal to 0. So what are the things that we have? So from the first law of thermodynamics, the relationship between internal energy change and work and heat is delta E equal to Q plus W. So now we know that delta E is equal to 0. Therefore, if we substitute here, we get Q plus W is equal to 0. From this we can say W is equal to negative Q. If heat is absorbed, expansion is done. If heat is lost, if heat is absorbed, compression is done. If heat is lost, expansion is done here. So now let's take the reversible expansion isothermal process. What is the formula for the work? That is equal to negative 2.303 nRT log V2 divided by V1. This is the formula for first law isothermal reversible expansion work. But here, do we have a final and initial volumes? No, we have a final and initial pressures. Therefore, I use the different formula, that is W equal to negative 2.303 nRT log P1 divided by P2. Now let's substitute here. W is equal to negative 2.303. How many moles of the gas was there? Here is the word, that is 1 mole. And let's take the energy R factor. If we report energy in the joules, R should be taken as 8.314. If we report energy in the calories, R must be taken as a 2 calories per degree per mole. So here I am taking 8.314 for joules times, what is the temperature given? 273 K times log, what is the final pressure? 0.1 divided by initial pressure is, the initial pressure is 1.0, that is numerator P1 divided by 0.1. So that gives us, so negative 2.303 times 8.314 times 273 times log of 1.0 by 0.1. So log 1 divided by 0.1 is 10 and log 10 value is 1. So what we have here? We have 273 times 2.303 times 8.314 times 273. So we have negative 5227.2 joules. So this is the work done in isothermal expansion. So what is the heat absorbed? Heat absorbed is equal to Q equal to negative W. So therefore Q is equal to 5227.2 joules. So this expansion is done by absorbing the heat. So this is the problem 2. Now let's go for problem 3. Okay, a sample of argon at 1 atmosphere and at 27 degrees centigrade expands reversibly and adiabatically from 1.25 decimeter cube to 2.50 decimeter cube. 1.5 decimeter cube is nothing but liters. So that means 1.25 liters to 2.50 liters. Calculate the enthalpy change in this process. And here molar heat capacity at constant volume is given for argon is 12.48 joules per Kelvin per mole. Okay, So what should we do here? Enthalpy change in this process. Okay. So delta H, we are going to find out delta H. And what else we require here? Okay, only enthalpy in this process. We are given CV and we need to find out delta H. Okay, what is the delta H formula? Delta H is equal to NCP delta T. And we know the initial volume and final volume. We know the initial temperature, and we don't know the final temperature. So therefore, as it is an adiabatic process, we should use the formula T1 divided by T2 is equal to V2 divided by V1 power gamma minus 1. Now let's substitute. What is the T1? 273 plus 27, that is 300 Kelvin, divided by T2 is equal to, what is the V2 final one is 2.50 liters. I don't use it because they will cancel each other, and divided by 1.25 raised to the power of gamma minus 1. What is gamma? So here is the hint. The hint is argon is a monoatomic gas. For monoatomic gas, gamma value is 1.66. Now let's substitute here 1.66 minus 1. So that makes 300 divided by 2 is equal to 2.5 divided by 1.25 is 2 power 1.66 minus 1 is 0.66. So that gives T2 is equal to 300 divided by 2 power 0.66. So if we do the maths, let me do it with the help of calculator. So I got 188.55 Kelvin. So another evidence for our argument in the last class. So in adiabatic expansion, there will be a cooling effect. So that is what it is observed here. So temperature drop from 300 Kelvin to 188.6 Kelvin roughly. But the question is not about the temperature, it is enthalpy change. And what is the enthalpy change? This is the enthalpy change formula. Here we should know how much gas is used here. So here, okay, let's use per mole is given. Therefore, let's take n equal to 1. And we don't know Cp. We have to find out. And delta T. What is the delta T? Let's see the delta T. Delta T finally is 188.55 minus initially what is the temperature? 300. Therefore, what do you get here? 188.5 minus 300. That's going to be negative 111.45. Okay. So this is the temperature change, Cp delta T. And we need to find out Cp. And what is the formula? Relationship between Cp and Cv? Cp equal to Cv plus R. Why I am taking this formula? Because in the problem, the Cv is given, but we require Cp to solve this problem. Therefore, Cp is equal to 12.48 joules over Kelvin mole. As the Cv value is in joules per mole per Kelvin, R value also must be taken in joules only, that is 8.314 joules over Kelvin mole. So that gives us Cp is equal to, if we add these two, 20.794 joules over Kelvin mole. Now we know the N value, which is 1 mole substance. Let's take for the 1 mole substance. We know the Cp value and we know the delta T value. And what are we going to get? Let's see now. Delta H is equal to 1 times, okay, let's find out what is the mass here. Is it n equal to 1 in this process? Okay, there is some doubt. This is a question mark here. Okay, and let's take one of the condition and let's apply ideal gas equation. What is ideal gas equation? PV equal to nRT. Before we do the enthalpy, let's find out the number of moles. So that is PV is equal to nRT. So from this I can write n equal to PV over RT. Let's take the initial condition. In the initial condition we are having, sorry, it is actually expansion, yes, okay. So 1.25 volume, and what's the pressure? 1 atmosphere divided by R value is, we know in the liter atmospheres, that is 0.0821 times what is the temperature? 300 Kelvin. So now we get N equal to, if we do the maths for this, 1.25 divided by 0.0821 times 300, that will be 0.05 075 moles. So this is the number of moles. So why I have taken n equal to 1? I don't know. Okay, that's a very bad thing to do. Okay, now we got n value, and what is the formula? Delta H is equal to NCP delta T. So that's going to be 0.05075, and what is the Cp? That is 20.794, and what is the temperature change? That is negative 111.45. And what are we going to get enthalpy change here? Let's see. 0.05075 times 20.794 times 111.45. So I got negative 117.6 joules. That's the answer. That's the enthalpy change. What is the negative indicating here? Enthalpy is decreasing. So final enthalpy is less than the initial enthalpy. Why it is so? It is expansion. In the expansion, the gas suffers cooling in adiabatic process. So that clearly indicating in the enthalpy decrease the gas. Okay. So these are the problems for the today's class. Thank you very much.